be Sepideh Mahabadi. She's a senior researcher at Microsoft Research in Redmond, and she's going to tell us about her work on diversity maximization in the offline and composable Coreset models.
Thank you. Hi, everyone. Thanks for coming. So today I'm going to start by giving you some backgrounds on diversity maximization problem and its applications in practice. Then I'll tell you about composable coresets and its application in other theoretical models of computations for big data. And for the technical part of the talk, I'm going to talk about our composable coreset results for pseudo-forests. It's a joint work with Shyam Narayanan. And finally, I'll mention some generalization of the problem to the constrained version of the problem and tell you about some experimental results that we have with my co-author Stoyan Troyanovsky at Microsoft. Okay, so let's see what diversity maximization problem is. We're given a set of endpoints in some metric space and a parameter k. The goal is to pick a subset of size k of these points with maximum diversity. Okay, so for some notion of diversity that we will talk about later. Okay, so why do we care about this problem? This problem comes a lot in, for example, summarization. Let's say you have a user and you want to populate a feed for that user. So there are a set of messages that from that friends of that user or from the channels that are posted in channels that the user is part of, and you want to basically show a summary of those messages to the user. Okay, and now in your summary, you don't want to have repeated messages. You want to have some diversity and in what you're showing to the user. It also has, like, in general, it has application for video summarization, like a set of images, documents, and so on. Okay, so it has application, for example, in search, where you want to make sure that the results of your search is diverse. In a recommendation system, let's say a user is buying some product and you want to recommend few other options to look at, or even like for candidates, you want to suggest a few candidates to look at, and you want to have some kind of diversity in what you're suggesting to the user. Okay, and in many other applications, this diversity maximization problem comes up. So usually in these applications, the objects that you have are mapped into points in a high-dimensional space or some other metric space. And now as input, we are given these points, set of points in some metric space. And let's see, what do we mean now by the notion of diversity? So what does it mean to pick a subset of diverse points? Okay, so in actually 2001, Chandra and Halderson introduced this taxonomy of diversity-based measures, diversity measures that are based on pairwise distances between the points. So I'll go over some of them to just see, for example, what are typical measures that people use in practice for diversity measures. For example, so the first one is basically minimum pairwise distance, which means that maximizing this notion means that I want to pick a subset of size k such that no two of them are very close. So I want to maximize the minimum pairwise distance between the set of points that I've picked. Okay. For example, if this is the set of points that I have and the orange ones are the ones that I picked, then the diversity between the set of points that I've picked is basically the distance between the two closest ones. Okay. So if I pick these 3 points instead, then the diversity is lower because there are 2 points now that are closer to each other. Okay. Is it clear? Any questions? Okay. So it's known that a greedy algorithm would give you a constant factor approximation for this problem. So people also consider sum of pairwise distances, notion of diversity, which is basically a more robust notion for diversity. It basically computes the distances between any pair of points and sum them up. So this will be what we measure as the diversity of a set of points. For example, for these 3 points, the sum of these 3 arrows is what we measure as their diversity. If we pick these 3 points, then we have, again, a lower diversity measure. And again, for this problem, it's known that the local search algorithm would give you a constant factor approximation. And so another notion, which is basically an interpolation between these two measures, is basically the sum of distances to nearest neighbors. So it's not as fragile as the first one, which only depends on two points, but it's also taking into account the minimum distances. So you sum over all the points that you have picked, their distance to their nearest neighbors. So for example, for this guy, this is the closest distance. For this one, this is the closest one, and vice versa. Okay, so this is what you measure as the diversity of a set of points. If you pick these 3 points instead, then this is like what you measure as their diversity. So again, this is like an interpolation between the first two measures. First, in 2001, Chandra and Halvorson gave a log k-factor approximation for the problem. Later in 2016, Bhaskara, Kadiri, Mirokti, and Svensson like improved the approximation factor to a constant using NLP. So there are like other measures. For example, what is the cost of the minimum perfect matching among the points that you have picked? So this is also one other notion that people use for diversity of a set of points. And basically, yes, for these 4 points, for example, this will be what we measure as their diversity. If you pick these 4 points, then the diversity is lower. Again, like Chandra and Halvorson gave a order log k approximation for this problem. And this was basically the best known approximation for the problem so far. Okay, so again, like there are all these other notions, like what is the cost of the minimum spanning tree, like a minimum TSP, star, and so on. Okay, and basically this was what we knew about these problems. And I also want to show to mention that this is basically the all the measures that are based on pairwise distances. There are also like some other measures that are not necessarily based on pairwise distances. For example, one of them is this volume, where basically given a set of endpoints, the goal is to pick a subset of size k such that the volume of the parallelepiped spanned by those k points is maximized.
Excuse me. You talk about the greedy algorithm. It's completely obvious what greedy algorithm you're talking about, or is it just the right greedy algorithm?
For what problem?
With many of them, you said the greedy algorithm works.
So I won't have time to go over all of them, but that greedy algorithm in particular, I'm going to mention.
Great.
Okay, again, for this problem, this is much harder. You cannot get better than some exponential factor approximation for the problem. But Nikolov showed that how we can actually achieve like e to the k over 2 approximation for the problem. Okay? And again, this is a higher order notion of diversity because it doesn't only depend on pairwise distances between the points. For example, if the points are linearly dependent, then you get 0. Otherwise, like it will be non-zero. Okay, so in a recent work, we actually close up the gap for the matching problem. So for the only remaining one here. So we improved the log k approximation to a constant factor approximation. Okay, so with that, let me move on to the composable coreset setting, which is basically a notion which is used for many of the massive data models of computation. So let's see what composable coresets are. So in particular, because many of the applications for diversity maximization need to handle large amounts of data, for example, summarization, searching, and so on, there has been a lot of effort that goes into solving these problems in massive data models of computation. And that's why we're looking at this notion of composable coresets, which is a powerful tool that at the same time gives you an algorithm in many other models of computation that concerns massive data. For example, distributed streaming and so on. Okay, so let's see what coresets are. A coreset of a data set is a small subset of it that represents the data very well. Okay, so what do we mean? It means that suppose that I have a data set and I want to solve a problem over that data set, then a coreset is just a small subset of it, such that solving the problem over the coreset gives me a good approximation for solving the problem over the whole data. Okay, so it's basically task specific. So if you are, you can think of it as you're given like some function that you want to optimize on your original point set. If optimizing f on this subset gives you some, let's say, alpha factor approximation, then we say that we have an alpha factor coreset. Okay, so this is basically a generic notion. Here we are looking at the notion of composable coresets, which is basically a coreset with composability property, meaning that the union of multiple coresets should be a coreset for the union of the whole data. Okay, so what do we mean? Suppose that I have multiple point sets v1, v2 to vm, and we want to come up with subsets u1, u2 to um, such that if I take the coresets and take their union, basically the value of this function f over the union of the coresets approximates the value of the function f over the union of the whole data, let's say by this approximation factor alpha. So if I have this property, I say that I have like an alpha composable coreset. questions?
Does it matter how many things you take?
No, it doesn't. So what we are looking at is basically what is the summarization algorithm. So at the time that we are creating this course, we don't know how many other data sets there will be and what will be those data sets. So yeah, good question. Okay, so now let's see why we care about this notion and how do they imply algorithms in other models of computation. Like a trivial application would be in a distributed, for example, MPC model, where your data is partitioned, let's say, over machine. Your data is very large, it's partitioned over machine. So what if you know how to compute a composable coreset? Basically, each machine can compute a composable coreset only on its own data and send it to a single aggregator. Okay? Because the size of the coreset is small, the total communication is low. And because of the composability property, the solution computed by the aggregator is a good approximation for the whole data. So let's see the application in the streaming setting. So in the streaming model of computation, you're receiving a set of elements on the in a stream, and you actually want to compute a solution on the fly using a small storage. Right? So basically, if you have a coreset for the problem that you want to solve, basically you can reduce this, the space usage of the algorithm from n down to square root 10. How can you do it? Basically, you can just divide your stream of inputs into chunks of size square root 10. And now you can start receiving the elements of the first chunk until you receive all of them completely. You store them in the memory. And once you receive the whole chunk, you just compute a coreset and then ignore the rest, but only the core. So you only keep the points that are in the coreset. And then you move on to the second chunk. You wait until you receive the whole chunk completely. At the end, you compute a coreset and ignore the rest. Okay? Until the end of the stream, where at the end, you just compute the solution of your problem to the union of these coresets. Again, because of the composability property, this is going to be a good solution. And this allows for the space usage of the algorithm to go down from n to roughly square root n, assuming the size of the coresets is small. Okay, basically, you can apply the same framework for like partially dynamic algorithm, basically in the incremental model, right? So once you receive one element, you can just if this completes the one chunk of your data, you just compute a coreset and keep the coreset. Basically, once you're given a query, you can just compute the solution on the union of the current chunk and all the coresets that you previously computed. Okay, so again, this allows for the size of the instance to go down from n to roughly square root 10. Okay. So they're not very good with deletions, but there's this notion of a robust coresets that allows to handle like up to L, let's say, outliers, which are basically the points that we are going to delete later on, and by adding an extra factor of L. Okay, and in general, like coresets has been used to basically generally to improve the runtime of algorithms using this partition and solve method in the context of similarity search and so on. Okay, so let's see what, so we've looked at this problem from the perspective of coresets as well. Basically, it was known how we can get like constant factor approximation for these problems or the log k factor for these two. And for the volume maximization, it's known basically how to get an order k to the k approximation, and it's known that basically it's tight. Okay, so note that the size of the coreset is roughly k, so it doesn't depend on the original number of points. So no matter what is the original size of the point set, you can always scale it down to k, while preserving the important information. Okay, and in our recent work, we basically showed that you can also get a constant factor approximation with the coreset of size k for the matching problem, and also like a coreset of size k to the 1 plus epsilon with approximation factor of 1 over epsilon. Okay? And this is basically the result that I'm going to talk about. Okay. Any questions?
Is it often the case that if you have multiple coresets, you can take a computer coreset out of that to reduce the size? If you have t coresets, you would have like size.
You can normally apply it in a recursive way, but each time you're losing some factor. Each time that you merge, you lose. Okay, so what we do here is that I'm going to show you how we can compute a composable coreset for the sum of nearest neighbor notion of diversity. Again, it's a joint work with Shyam Narayanan. And the statement is as follows. So there exists a composable coreset of size k to the 1 plus epsilon with approximation factor of 1 over epsilon for the sum of nearest neighbor notion of diversity. That is basically for a subset of size k, we define its diversity to be the sum over all the elements in that subset, its distance to the nearest other points that we have picked in that subset. Okay, so just to remind you, this is the notion that we are looking at. Okay, just a reminder. Okay, and again, we are in the composable coreset setting, meaning that I just want to compute, I want to come up with a summarization algorithm that given a point set can summarize it for me so that later on we have this composability property. Okay, so first I'm going to tell you about the greedy algorithm, which is basically a common algorithm used in this context a lot. And then I'll show a simple algorithm that gives me a coreset of size k squared, and then I'll tell you how we can improve it to k to the 1.5. I'll not mention how to improve it to k to the 1 plus epsilon, but hopefully I can say some idea about it. Okay, so what is the greedy algorithm? So given a set of points, the greedy algorithm goes for k iterations, and at each iteration picks the point whose minimum distance to all the points that you have already picked is maximized. Okay, so for example, it's first chooses some arbitrary point, C1, and then it picks the point that is furthest away from C1. And then at the third iteration, it picks the point whose minimum distance to C1 and C2 is maximized. And it continues for k iterations. So now it has like some nice properties. For example, if you let R to be the minimum pairwise distance between the points that you have picked in this procedure, then what we know is that everyone else that you have not picked is within distance R of someone that you picked. Okay, so pictorially, if the minimum distance between these three centers that you already picked is R, then it's basically easy to check that everyone else is within distance R of someone that you have picked. Otherwise, in the last iteration, you should have picked someone else. Okay. And so what does it mean? It means that basically I can cluster all the points into k clusters in a way that the distances within each cluster by triangle inequality is at most 2R. Okay, so now let's see how using this we can get a simple coreset for of size k squared. Okay, so the coreset algorithm is going to be very simple. It's as follows. We just run the greedy algorithm, and it gives us this set of k clusters. From each cluster, I'm going to pick k points, k arbitrary points. That also includes the centers. Okay, so I run this algorithm. I first pick the centers and put them in my coreset, and then I'll pick k minus 1 other arbitrary points from each cluster and also put them in the coreset. So it's trivial that the size of this coreset is k squared because you have k clusters and you're picking k points. And now why does it actually give you a coreset? You need to say that basically for any optimal solution, you can replace them with someone from the coreset such that the overall diversity does not decrease as much. Okay. So here there are two cases. So the first case is that if the optimal solution itself, the value of the diversity for the optimal solution itself is smaller than 5kr, then we argue that basically the centers themselves that we put in the coreset have large diversity. Okay, why is that? Because basically for each point in the each point of the center that we picked there, because the minimum pairwise distance between the centers is R, the distance of everyone to their closest neighbor is also at least R. Okay, so basically we are summing over all the points among the centers, their distance to the nearest neighbor. So it's going to be at least R times k. So this will give us like a 5kr approximation. So the other case is basically when the value of the optimal solution is at least 5 times k times r. But basically in this case, it's okay to move anyone from the optimal solution to someone within distance 2r, because this way the distance between any pair of points only in the optimal solution only changes by 4 times r. So the total value of the diversity function only decreases by 4 times k times r. But because the optimal solution has value 5 times k times r, this is going to give us like a factor 5 approximation. Okay. So now what we will do is that we will look at the points in the optimal solution, and we are going to replace any like if there are ki points in cluster I, we are going to replace those ki points from the optimal solution with an arbitrary set of ki points from the coreset. Okay, so pictorially, the green points here are the optimal solution, and the red points here are the points from the coreset that we computed. So what we do is that we are going to replace any point from the optimal solution with someone from the coreset. And basically, by what we just argued, like the diversity of this set of points is going to be roughly the same as the diversity of the points in the optimal solution.
So the reason you needed to pick k per cluster is so that you have enough to like replace.
Exactly. Yeah. Exactly. Yeah.
How can you ensure that there are at least k nodes in each cluster?
So this is how we picked our algorithm. So we included, so in the corsets, we first run this greedy algorithm, and from each cluster, we included k points in the coreset. So
You just include all the points?
Well, then even in the optimal solution, there can't be, yeah, exactly. Okay, so these are all good points. Okay, so now let's see how we can improve this coreset size. As you just mentioned, like, why do we really need to keep k points from each of these clusters, right? So in particular, so the reason we might need them is that maybe we want to match. There are more than one point in the optimal solution that we want to match with, and we don't have enough of them if you just pick like a single point or a constant number of points. So let's take a closer look. Basically, now there are 2 kinds of optimal solutions. There are these points in the optimal solution that are in clusters, which at most, there is at most 1 point from the optimal solution. Let me call them opt1. So there's only a single optimal solution in this cluster. And then there are these opts greater than 2, which are basically the subset of the optimal solutions that are in the clusters, which there are more than 1 point from the optimal solutions. Okay. So they're pictured here, some examples. Okay, and a simple observation is that basically the points that are in the second group, opt greater than 2, does not contribute much to the value of the objective function. So because there's another point from the optimal solution there, the distance to the nearest point is at most 2r. So they're not contributing more than 2r to our objective function. So we can basically more or less, we can roughly ignore them. Okay? So we can move them anywhere else as long as they're not ruining the contribution of the points that are in this opt1. Okay? So if I move someone from here to someone close by here, I'm also ruining the contribution of this point, which I don't want to do.
Little embarrassing way. So when you draw these things, the clusters, the C1, C2, C3, they're well separated from each other, but in principle they could overlap a lot, right? I mean,
no, I'm basically connecting everyone to their closest neighbor.
Okay.
Yeah. So each point is clustered to the closest. Yeah. Okay. So now suppose that hypothetically I had some points in my coreset somewhere very far from the optimal solutions. Okay, so then, no point from the optimal solution is therefore here. So what I can do is that I can just pick one center, 1 point from each cluster, and I'm going to match as much as I can inside the clusters and move all the excess points there. Okay, so k is a subset is a set of points in my coreset of size at least k. So I can move everyone that is excess over there. So it does not ruin the contribution of, for example, C2. So the problem with this, so this is all good. So basically, now I replace these points in the optimal solution with these guys, so the diversity does not decrease. So the only points, so the only negative part is that basically such a set S may not exist. So what instead I'm going to do is that I'm going to use the power of two sets of var points. So in particular, it's only enough to keep k points from either C1 and C2. Okay, and the algorithm would be just as follows. Just run the greedy algorithm, keep the center of all the clusters, plus also keep k points from C1 and k points from C2. Okay, instead of picking k points from each of them. And basically, why does it work? Basically, the distance of C1 and C2 is roughly the diameter. Okay, so now what we can argue is that we can now move all the excess points to all of them either to S, to C1 or C2. Okay, and I'm going to choose this uniformly at random with probability a half. So now the contribution of everyone else is preserved with probability a half. So half of the contribution of each point is preserved with probability a half. Okay, so again, pictorially, so this is C1 and C2, the distance is roughly the diameter. Now for any other point in the optimal solution, its distance to either C2 is larger than the diameter or the distance to C1 is larger than the diameter. So because we are picking one of these two with probability a half, we are preserving half of its contribution with probability a half. So either C1 or C2 is going to be a good option for us.
I forgot, how did we define C1 and C2?
So these are the first two clusters. Right. So you run the greedy algorithm, it gives you a set of centers, and now you look at all the points that are closer. Their closest center is C1, and their closest center is C2. Okay. Okay, and we also know that the contribution of the optimal solution cannot be larger than the diameter. So this gives us a constant factor approximation. Okay, so there's another problem with this, and the main problem is that basically C1 and C2 themselves may not have enough points, so they may have much less than k points. Okay, and then how do you want to proceed? Basically, do you want to continue with C3, C4, and so on? And it's not clear like if that will work. So what we will do instead is the following: we will basically show. So this will be our goal from now on. So you can forget about everything else. So here is a problem. So you're given a set of endpoints in some metric space, and you want to find two subsets, each of size k, such that their distance is maximized. Okay. So the problem is clear. So we're given a set of endpoints. The goal is to find two sets, each of size k, such that their distance is maximized. How do you do it? Okay. And basically, the reason why this is enough is that again, we can argue that we can move all the excess points to either S and T chosen uniformly at random, and one of those options will work for us. Okay, the same reasoning as before. Okay. So let's focus on this, and let's see how do we find it. And in fact, what will be the maximum distance between two sets S and T? Okay, so it turns out that basically if you define r hat to be a radius of the smallest ball that contains at least n minus k plus 1 points, then this is basically the distance that you're looking for. So there exist sets S and T such that their distance is approximately r hat. Okay. In fact, it's like easy to show that you can't get better than that. But but it's not clear like if that value is possible to achieve. And here is what we showed basically. So let's see how we can find two sets, S and T, each of size k, such that their distance is roughly r hat. Okay. So here are a few cases. So first of all, we assume that the total number of points is at least k to the 1.5. 2 times k to the 1.5. Note that if this is not the case, we can put everyone in the corset, and that will be all good. So the first case is the following, basically. The first case is where there exists a point x, such that within the ball of radius r hat over 2 of it, there exist k points. Okay? So why we are good in this case is that basically we know that outside of the ball of radius r hat around x, there exists at least k points. Otherwise, this would contradict the definition of r hat. We would have found a smaller ball. Okay, so now there are k points inside, there are k points outside. I'm going to let the inner points to be s and the outer points to be t. I know that the distance is at least r hat over 2.
Sorry, what was the contradiction? Because like your r hat is for n minus k plus 1 points, and so yeah.
Yes. So if basically if there are not enough points outside, then you would have found a smaller ball.
Is it supposed to be outside the ball then in the definition, or is it inside? Like the definition of r hat that you have at the top.
No, this n minus k plus 1. Yes. So this is inside, but this would also mean that there are k points outside.
Oh,
around the ball.
Okay, I see. Yes. Yes.
Yeah, the reason I define it this way is because of the points on the boundary. So
Okay.
Okay, so otherwise, we're in this case where basically for each point x in my in my data set, the ball of radius r hat over 2 around it contains less than k points. Okay, so now there are 2 cases here. So the first case is that basically when the majority of the points have at least square roots k number of points around them within the ball of radius r hat over 4. So why we are good in this case? So let me move the picture up there. So in this case, what I can do is that I'm going to randomly sample square root k of these centers, and now in the set S, I'm going to put those centers plus everyone that is within distance r hat over 4. Okay. So because I assume that there are at least square root k points within distance r hat over 4 of most of them, majority of them, then I'm going to get enough points from this sampling. So I'll get at least k points. And so now what I'm going to do is that I'm going to remove everyone that is within distance r hat over 2. And basically this means that and now I need to argue that basically there are at least k points outside of these balls that is remaining for me that I can choose to be in the set T. Why is that? Because I only sampled square root k points. Each of them has at most k points in the ball of radius r hat over 2 around them. So if I just remove these points, because the value of n is at least k to the 2 times k to the 1.5, I get that there exists at least k points outside of these balls. Okay, so I can just let this set be the set T, so that, and I know that the distance between S and T now is at least r hat over 4. Okay, now the final case. The final case is basically when the majority of the points have less than square root k points within distance r hat over 4 of them. And in this case, what I'm going to do is that I'm going to, from that majority, I'm going to choose k of them. So I'm going to pick k of those points, and that will be my set S. So there are k points. And I'm going to remove everyone that is within distance r hat over 4 of them, so everyone that are in these balls. And why does there exist k points outside of these balls? The reason is that, again, I had only k balls. Each of them contained less than square root k points. So the total number of points that I removed is going to be at most k times the square root k. So I get enough points outside of these balls. So again, I can pick k of them. So this is going to be the set S. These are going to be the set T. And the distance between them, again, is at least r hat over 4. Okay. So basically, this will give me the result that I want. So if the number of points is at least k to the 1.5, then we can find S and T with distance roughly r hat over 4. And one can show that basically one can generalize this idea to the case where if the number of points is larger than k to the 1 plus epsilon, you can get 2 sets whose distance is roughly epsilon times r hat. Okay, so now that we solved this intermediate problem, so let's see how we get a corset. So the corset will be as before. So if the number of points is smaller than n to the if n is smaller than k to the 1 plus epsilon, we're going to put everyone in the corset. Otherwise, we can just run the greedy, compute the clusters, include the centers of the clusters in the corset, and then using the previous algorithm, we just find S and T and put those sets S and T also in the corset. Okay, so it's easy to show that this also satisfies the composability property. So this corset is also composable, and so this will give us a corset of size k to the 1 plus epsilon with approximation factor of 1 over epsilon. Okay, so this finishes this part of the talk. So in the last few minutes that basically. A question that we think should be doable is basically if we can get a tight result here, like a constant factor with a corset of size k, order k. Okay, so in the remaining part of the talk, I'm going to briefly mention some generalization of diversity maximization problem to the constraint setting. And so this is basically a joint work with Stoyanovsky from Microsoft. So let me tell you about this generalization of the problem to the constraint setting. Okay, so we're looking again at the diversity maximization problem, but now the set of points that we have are partitioned into some groups. Okay, and now we have this additional constraint that from each group in our summary, from each group we want to pick a certain number of points, let's say ki. So the same problem on the partition constraint base. Okay, so we are given this partitioning. We also given instead of us being given k, we are given k1, k2 to km. So m is the number of groups, and we want to satisfy that in our summary. We want to pick ki points from group I, such that the overall diversity of what we choose is maximized. Okay, for example, here. Previously, we only had k, which was equal to 3. So this is what we would have picked. But now that solution is no more feasible. We want to pick only 1 point from here, and 2 points from here. So this will be maybe the solution that maximizes overall diversity, also satisfying the constraint. Okay. So why do we care about this problem? Again, for example, one application of it would be to incorporate recency of the messages. Okay, so each message in the feed generation scenario, each message comes with a posting time, right? So as the messages get older, we want to include less of them. So the summary we have is basically we want to incorporate recency into the summary that we have. So what we can do is that we can basically partition the messages into batches based on their time, and then we want to assign less budgets to the older messages. Okay, so. We want to basically, for example, the messages in a month, we can partition them into 4 weeks, and we want to have more messages from the current week in the summary that we are showing to the user. Okay, so let's see what is, so this is known as either fair diversity maximization or constraint diversity maximization. And let's see what is known for the problem. For the notion of minimum pairwise distance, at the Connie, McGregor, Meliu, and Mumulito basically gave an m+1 approximation for the problem. For sum of pairwise distances and sum of nearest neighbor notions of diversity, the algorithms that worked for diversity maximization also worked for, under the partition constraint setting as well. So one question here would be if one can get like a constant factor approximation for this problem. And so if in the corset setting, basically, the work of McGregor et al. Implied a corset of a constant factor approximation with only order k number of points from each group. For the sum of pairwise distance notion of diversity, there was like an algorithm that was giving like a good 1 plus epsilon approximation, but the total number of points in the corset was large. It either depended on n or the aspect ratio. So in a recent work, we basically showed how we can get like a corset that is totally independent of the initial number of points. So we were able to improve the size of the corset down to ki squared. We also show similar results for the other notion of diversity, but here the approximation factor again is not tight. So one other open questions would be if we can get tight results here. Okay, so in the last slide, I'll just mention some experimental results that we have for this problem. Basically, as we expect, we run this if you just, basically the first experiment says that if you just run diversity maximization on this set of messages, what you get does not respect recency, but this is what we expect. So there is a need for defining this notion of constraint diversity maximization in order to incorporate for recency of the summary that you have. And the second is basically computes the price of balancedness. So how much do we lose by resorting to the constraint version of the problem, fair diversity maximization, as opposed to normal diversity maximization. For sum of pairwise distances, the loss is only 1%. For sum of nearest neighbor distances, 20%. And for minimum pairwise distances, 50%. So basically, this you can also see this interpolation of this notion between the two in this experiment as well. So basically, this minimum pairwise distances is very fragile. So you actually see a lot of loss in the diversity when you resort to the constant version of the problem. And the final set of results shows the power of corsets. Basically, so using the corset, you don't need to recompute your summary for the past data. You can actually reuse it. And by doing that, it allows you to improve the runtime of the algorithm by a factor of 100 in practice. That's a lot. This basically only, and this is done by only losing on diversity by a few %. Okay. So I'll stop here. I've marked the open questions here, so if you want, I'll be happy to talk about them. Yeah, thank you for coming.
We have time for a few quick questions.
Yeah, I was curious where the 1 over epsilon came from then, because like you didn't quite get to explain that, or what is the like this distance?
So we need to.
Can you repeat the question so that?
Sure. So the question is basically where does this 1 over epsilon factor in the approximation comes from? And the answer is that, so I didn't go into like the result that gets like k to the 1 plus epsilon, but basically you need to have this nested set of points, and the ratio of each of them is the number of points in each of them increases by a factor of k to the epsilon. And basically the distance, therefore, is only 1 over epsilon, is just epsilon times the total distance of our hat. So you're partitioning it into like some nested sets. The distance between any two adjacent one is only epsilon times the total distance.
Yeah, 2 questions. One is, when you did those experimental results, what is the, I mean, there are these metric measures, but what exactly do people care about when they're trying to read messages? Like what is the
diversity measure, you mean? What do
yes, these are proxies for diversity that you care about.
So it really depends on the application. For example, like for the video summarization, people use a lot this DPP notion, this volume. Also for I'm aware that for some practical work, also like for summarization of a set of messages as well, like people try different, and like there's a slight preference towards volume as well. But I'm also aware that both of these minimum pairwise distance and sum of pairwise distances is used in applications. And like also the work by Bhaskara, Qadiri, Mirokni, and Svensson argued that there are some applications for which this distance to the nearest neighbor is what works best for some applications. So.
The second question is about the choice of k. You know, most of these algorithms sort of like kind of use k in the design of the algorithm or the construction of the coreset. So that is k. I mean, you know, can one take some of these constructions and like not rely on k in some nice way, or because k may change, or how sensitive are they to k? The choice of the
Sure. Yeah. The question is basically whether the choice of k is kind of strict, or it can change, and the algorithm also can be flexible with respect to that, right? So some of the algorithms are flexible. You can just continue further. For example, the greedy algorithm, it will just be the continuation, right? But the local search algorithm, you really need to run it with the new k. On the practical side, And there are many applications that K is somewhat fixed. For example, how many results do you really want to show to the user, let's say, in the first page of the search? Right, so this is going to be your K. And if they want to go further to the next pages, then you have like further values of K, but it's not something that changes.
I was wondering, could you tell us what the order of 1 terms are in this table?
And for which ones? For example, the initial is diversity, like the basically offline diversity maximization. These are constants less than 5. The one we gave here, I believe it's like 16, which might be the largest. Yeah.
Okay. We'll take any remaining questions offline. Thanks.
Yeah.
We're going to be having the lunch break.